I'm Mike Jiang. I work with Rafael Gurtado in Gurtado Lab in Fred Hutchinson Cancer Research Center, and we mainly develop the statistical tool and software tools for the high throughput biological data assay. So for single cell data, we did some of the benchmarking for the OnDix file formats, and let me move on to the summary. And I think Rafael should be on the call, and he will jump in anytime during my presentation. So everyone's talking about HDF5 based storage, and that's what we are aiming for. Try to benchmark H5 against other alternative on-disk formats to see if we can find a most best format for the single cell assay, and if HT5 is indeed the best, and how we can squeeze the most speed by improve the usage of the HDF5. So basically, we benchmark H5 against the conventional database like Sqlite, and also cloud-based HSDS, which is now branded as Kita. It has nothing to do with the H5 library, but it's the cloud-based distributed storage. And also we look at the tiledb, which is another scientific library, open source library for tailored for the data matrix storage. And also we want to see how we can improve H5 by different approaches, and provide generic benchmark tools to do the further exploration for the more data formats. And first of all, we look at the Sqlite and H5, and we did some of the similar data using the beta distribution, and use a different size of the data set. We tried to fix the number of genes as 30,000, and we increased the number of cells from 1,000 all the way to 100,000, and we tried to get the specificity from the 70% to 92%, and kind of similar to what we have seen in the 10x data 1 million neuron data set. And so we also use the in-memory version of the data matrix and a sparse matrix, and its compressed sparse row format as the reference to compare with the other OnDix format. For the H5, we use the 2D dense format, compressed by the default gzip compression, and chunked by row, which is gene-wise. And we also try to see, as Mike Smith mentioned, that HyperSlab has the issue, and then we try to see how bad is this and how we can improve it by only accessing the H5 data through the chunked data. And for the Sqlite, we use the CO, which is a coordinate list, basically store each data point as the coordinate X, Y, and actual value. And an access pattern, IOX pattern, we try to access basically every kind of upstream data packages mentioned previously, boiled down to the three kind of access pattern: row-wise and column-wise, and random slicing through the both row and the column. And so here is the actual plot. So as we can see, the H5 default H5 HyperSlab selection is pretty slow. The green, I think the green is the H5, but the Sqlite is only working for the smaller size, both row and column-wise random sub-matrix random slicing. When it comes to the entire row and column-wise selection, and the coordinate-based storage in the database won't work well. simply it's not tailored for that. Next, we try to mimic what H5 does for chunking, and the Sqlite, we store each row as a single binary blobs, and we only access the entire gene or entire row instead of each dot. And that seems to be improving row-wise and column-wise selection. But the random slicing is also equivalent, comparable to what H5 can achieve. So that means the H5 is still working quite as good as the Sqlite. So next, we move on to the cloud-based solution, HSDS, and with some help from Jiang from HDF Group, I got access to their cloud server system, and we use the smaller single-cell assay, which is flow cytometry. It has the 480,000 cells, but has a less number of features, which is 22 columns. And we keep chunk size proportion to the original data matrix shape, which is about a 1/4 size of the original data set. And access pattern, try to mainly focusing on the random slicing, and which is a point selection in the HSDS terminology. And so from this plot, we can see the cloud-based distributed storage is more scalable than the native H5 local storage for the random slicing. Even we consider the overhead from the network internet latency, we still see the cloud-based system is, especially when you increase size of the random sliced subset. And as previously mentioned, that's mainly due to the hyperslab union selection overhead from the HDF library. And we are yet to test a bigger data set to see how the cloud-based storage can perform when we increase size of the subset. And next, we move on to the tiledb, and this time we use
probably about 1 minute, Mike.
Okay. We use the 10x data, a subset of the 1 million neuron, 10,000 cells, and 27,000 genes, and you chunked by genes. And the same concept in tiledb has a tile shape. We use the same chunking size, and we tested both. tiledb has both format to offer: dense format, sparse format. And as we see, this tiledb perform better than the native hyperslab selection-based H5 disk I/O. Now, when we come to improve on the HD5 format, we can try to manipulate the chunking shapes. As we see, no matter how you tailor the chunking shape, and if your access pattern is different, not proportional to the chunking shapes, you're gonna get worse deteriorated format. And just one more slide. And so we come up with the hybrid approach. So we chunk by both cells, both row and column wise. And as we see this plot, the hybrid approach significantly improved the access speed, because we've dispatched the query request to the proper copy of the underlying data matrix format based on the actual shape of the query. So I guess my time is up. And I think lastly, I summarize, our next step is to further benchmark on the tiledb and for their native support of random slicing in the next release, and especially their integrated parallel I/O, And also we want to improve the a single cell experiment, which is delay array backend and support for the mass package. And also we work on the Bioconductor paper that's collaborate with the Stephanie. Thank you, everyone.
Thanks, Mike. That's great. Our final presentation is from Vince Carey.